Hello, good evening.
Good evening, sir.
First, let me show you your assignment. I got only assignment of Atif. Your first answer was correct. Second, also correct. There is some little mistake in this third part. You have to take room temperature, and in general, room temperature is taken to be 27 degrees Celsius. Okay, Atif?
Okay.
So that temperature difference will be 73. Then if you put this term in this formula to get alpha, you will get 6.021 in 10 to the power minus 5. And in last question, you had given percentage increase in length is 2%. So we may write it as delta L by L into 100 equals to 2. So move this 100 to right side. So delta L by L will become 2 by 100. Alpha is given. So according to the formula, alpha equals to delta L by L times delta T. So we have to calculate temperature difference. So move this delta T to left side and alpha to right side. This particular delta L by L is 2 divided by 100. Alpha is given. If you simplify it, you will get 1000 degrees Celsius. Is it clear?
Yes, sir.
Okay. Ribasha, there was a little mistake in this particular calculation. When you take a particular numerical value, just try to convert each quantity in same unit. If you are calculating in terms of SI unit, convert all term in same SI unit. You have taken force in Newton and rest of the whole term in CJS unit. I will give you the actual result or correct result. Okay, Riba?
Yes, sir.
Rest is correct. Okay. Do you have any doubts from last class to any one of you?
No, sir.
Atif, any doubt?
No, sir.
Okay. In last class, we had defined linear expansion of solid on increasing or decreasing temperature. Next, aerial or superficial expansion. Suppose you have a rectangular sheet. Having initial length L0 and breadth B0. So if you raise the temperature of this particular rectangular sheet, there will be expansion in all direction, in length as well as in breadth. So whole of its area will increase. So it may acquire this particular shape. So that length would become L and breadth B. So for this part, we may define some other rate of expansion of solid in terms of area, which is called beta. Temperature coefficient of aerial or superficial expansion. And in terms of change in area, we may define it as beta equals to change in area divided by initial area times change in temperature. So SI unit using this relation for beta will be Kelvin inverse or degree Celsius inverse. Is it clear? Abhinav,
Yes, sir.
any doubt?
No doubt, sir.
Now for this part, since delta A divided by A is called fractional change in area, and this delta T is change in temperature. So we may define this beta as the ratio of fractional change in area to the change in temperature is called beta. So this beta actually defines you at what rate with respect to change in temperature, area of this particular sheet is expanding or contracting. So you'll say it defines the rate of change in area with respect to change in temperature. So if you expand this particular formula to get final area at any temperature T, let me simplify it as beta equals to delta A divided by A naught times delta T. So just cross multiply, you will get delta A equals to beta times A naught delta T. Delta A is nothing but final area minus initial area, beta A naught times delta T. Move this A naught to right side. So A will be equals to A naught beta A naught delta T. Now take out common A naught. So you're left with 1 plus beta delta T equals to final area, which is similar what we have obtained for final length in terms of linear expansion. Riba, is it clear?
Yes, sir.
Okay. Just write it down.
So can you scroll a bit down?
You all have written?
Yes,
Rishan
sir.
Mirza?
Yes, sir.
Okay. So related to this expression, you'll be asked first question to define relation between alpha and beta. Relation between alpha and beta. So according to the above expression of rectangular sheet, let's say this particular equation to be first. So we may write as length equals to L naught 1 plus alpha delta t as equation first. Breadth is also length. So we can write in terms of expansion of length. So it will be B naught 1 plus alpha delta t. Now, if you multiply these two expressions, you will get area. So on multiplying L into B equals to L naught B naught 1 plus alpha delta t times 1 plus alpha delta t. Since these two brackets are same, each having exponent 1 and 1, so we may write it as L naught B naught 1 plus alpha delta t raised to 2. Now this particular product L into B and this particular product L naught B naught be nothing but area. So it will be final area and it will be initial area A naught. According to binomial expansion, we can write using binomial theorem. If you have 1 plus x raised to n, in which x is very small as compared to 1. So this will be equal to 1 plus n times x. It means This exponential raised to this entire term may get multiplied with x part. Similarly, in this part, 2 will get multiplied with the coefficient alpha delta t. So we may write it as 1 plus 2 times alpha delta t. Now, let's say this particular equation is equation 2. Abhinav, is it clear?
Yes, sir. Clear, sir.
Good. Now, on comparing equation first and equation second, just compare these two equations and define, is there any relation between alpha and beta? Nida, try to compare. This equation and this equation. We have same point TA in left hand side in both these two equations. Same term A naught as coefficient of this part. So in this term, we have delta T attached with beta. Similarly, in this part, 2 alpha attached with delta T. So on comparing, we can say beta equals to 2 times of alpha. Is it clear? Atif?
Yes, sir.
So from this, we can say on comparing, beta equals to 2 times of alpha, or alpha equals to beta divided by 2. So this is the relation between alpha and beta. Rishan, is it clear? Just write it down till this part. You all have written? Atif, done?
Yes, sir.
Done, sir.
Suppose you have a rectangular sheet from which a hole is cut out. So you'll be asked, on heating both, how will size of hole and its cutout portion be affected? Will the size of hole and its cutout portion will expand, hole will start shrinking and its cutout portion start increasing, or vice versa? Riba, any guess what will happen?
The hole will shrink.
Okay, hole will get shrink and its cutout portion will start expanding.
Yes.
Okay. Abhinav, do you want to change this answer or you'll go with this? Atif?
Sir, I think the hole will shrink and the cutout portion will expand.
Okay. Just think one. Suppose you have this entire solid in which I've just marked a particular point. Let's say this. I haven't cut out. So what will happen on increasing temperature? So you'll say this entire system will expand. So say this entire sheet will expand. So this dot dot marked position, according to this, will also expand. Just think why it is expanding. So according to the concept I had defined in the first part, on heating, separation between particle increases due to increase in thermal kinetic energy. So let's say hole is like this, in which there will be some particle at its boundary. Let me define you. Suppose this is your hole on which particles are arranged initially like this. In solid, there will be least separation between particles. So if you start increasing temperature, what will happen? The separation between particle increases or decreases? It will increase. And since And at this condition, there is no enough space between these two particles to go towards one another. So separation between them must increase. So on increasing their separation, this particular geometry may acquire this particular shape. Okay, so you say both its cutout portion and its whole portion on heating will expand at same rate. Is it clear?
Yes, sir.
Riba, is it clear?
Yes, sir.
So in this part, we can say, since there is no enough space in between particle, so they won't go towards one another to get shrink. So on heating, both hole and its cutout portion will expand at same rate. Abhinav, is it clear?
Yes, sir.
Niba, any doubt?
No.
Okay. You all have written? Rishan, done?
Yes, sir, done, sir.
Let me ask you another question related to this part. Suppose you have a rectangular sheet in which there are two different holes. Let's say this particular position is A, this position is B, this position is C, and this position is D. On heating, how will separation between first A and D, second B and C will affect it? Just all of you just think and send me your answer. Good, Atif. Reba, just think again. Abhinav, any guess? Tell me. Will the separation between A and D increase, decrease, or it will remain same? Let me define you. Since according to heating concept, there will be expansion in this particular entire term. So there will be expansion in this first hole as well as in second hole. So separation between A and D will increase. What will happen between B and C? Suppose initially there will be a number of particles stacked together between A and B and C like this. So if you raise its temperature, will the separation between particle between B and C arranged like this will increase or decrease? Reba? On heating, separation increases. So you will say this particular separation initially between B and C will now expand up to this part. So in both cases, A and D and B and C, separation will increase. Is it clear? Atif, any doubt?
No, sir.
Riba? So in both cases, separation between them will increase. Rishan, done? Okay, similarly, we may define third part in volumetric. Volumetric or cubical expansion. Suppose you have cuboid having initial length L0, breadth B0, and height H0. So if you raise its temperature, it will expand at same rate from its all side. So it may acquire this configuration. So length will become this, breadth and height. So to define this particular expansion in volumetric, let me define another coefficient of temperature, which is called gamma, temperature coefficient of volumetric expansion. So this gamma in terms of volume will be change in volume divided by initial volume times change in temperature. So SI unit related to this formula will be Kelvin inverse or degree Celsius inverse. So we can define this gamma similarly as we define for alpha and beta. It is nothing but the ratio of fractional change in volume to the change in temperature. Or you'll say it simply defines the rate at which volume expand or contract with change in temperature. So it defines the rate of change in volume with respect to change in temperature. Abhinav, is it clear?
Yes, sir.
Okay. So similarly, if we expand this particular relation, you will say gamma equals to delta V divided by V naught times delta T. Just cross multiply. So delta V equals to gamma times V naught delta T. Delta V is final volume minus initial volume, gamma, initial volume times delta T. Move this V naught to the right side. So V equals to V naught plus gamma V naught times delta T. Now take out V naught as common. So it will be 1 plus gamma times delta T equals to final volume. First, write it down to this part. Then I'm defining different conditions. You all have written? Abhinav, Dan,
Yes, sir.
Nida? Okay. So we may write or define gamma in terms of alpha. So relation between alpha and as length equals to 1 plus alpha times delta t according to linear expansion. Similarly, breadth equals to b naught 1 plus alpha times delta t, and height equals to h naught 1 plus alpha delta t. Now, if you multiply these three dimensions, we'll get volume. So on multiplying these three terms, length, breadth, height equals to L naught 1 plus alpha times delta t, b naught 1 plus alpha times delta t times h naught 1 plus alpha delta t. So if you simplify this particular expression, L naught, B naught, H naught, 1 plus alpha delta t, we have 3 times. So it will be 1 plus alpha delta t raised to 3. Now this particular product will give you final volume, this initial volume. So we may write it as final volume equals to initial volume 1 plus 3 times of alpha delta t according to binomial theorem. So let's say this is equation 2 and this is equation first. So on comparing, again, we can say gamma will be equals to 3 times of alpha. So on comparing equation first and equation second, 3 times of alpha equals to gamma, or alpha equals to gamma by 3. Riba, is it clear?
Yes.
Okay. Now we have calculated alpha in terms of beta and alpha in terms of gamma. Now let me define your relation between all these three terms together. Alpha is one-dimensional, so divided by 1. Beta is two-dimensional, so divide by 2. And gamma is three-dimensional, divide by 3. These all three should be equals to 1. We may write this particular expression in some other way as also. Take the LCM of its denominator. So it will be 6. Multiply each part. So it will become 6 alpha, 3 beta, and 2 gamma. So this ratio will be also like this. So this is the relation between these three coefficients of expansion, alpha, beta, and gamma. Atif, any doubt?
No, sir.
Okay. You all have written? Ishan, done? Abhinav?
Yes, sir. Done.
Okay. If coefficient of expansion of radius in sphere is 2 into 10 to the power minus 4 Kelvin inverse. Find fractional change in volume if temperature is raised by 100 degrees Celsius. Try to find Atif, just check your calculation. We have given coefficient of expansion in radius. So it should be linear expansion. It means you have alpha equals to 2 into 10 to the power minus 4 Kelvin inverse. So to find fractional change in volume, which is three-dimensional, we must need gamma first. So according to the formula, gamma equals to 3 times of alpha. Then gamma equals to delta V divided by V times delta T. So from this, we can say delta V by V equals to gamma times delta T. Change in temperature is 100 degrees Celsius. Gamma we will solve from this part. Just multiply it. Atif, try to simplify. Three times alpha. Alpha is 2 into 10 to the power minus 4. So on multiplying, it will be 6 into 10 to the power minus 4. Now put this in this. So it will be 6 into 10 to the power minus 4. Change in temperature is 100 degrees Celsius. So on multiplying, you will get 6 into 10 to the power minus 2 or 0.06.
So should we not convert Celsius to Kelvin?
Okay, you are doing this. Suppose we have a relation between Kelvin and Celsius. K is equals to 273 plus C. So if you have to calculate change in Kelvin, let's say initial temperature is 27 degrees Celsius and some final temperature is 100 degrees Celsius. For this, if you calculate in Kelvin, it will be 300 Kelvin. And for this, if you calculate in Kelvin, it will be 373 Kelvin. Now, since we have to calculate difference of these two quantities, so if you subtract these two terms, you will get 73. And similarly, if you subtract these two terms, you will again get 73. It means difference in temperature in both Kelvin and Celsius, it will remain same. So we don't need to convert. Okay, Atif? Okay. Abhinav, any doubt?
No, sir.
Riba, is it clear?
Yes, sir.
Okay. You all have written?
Done.
Now, on the basis of this volumetric change, we may define temperature dependency over density of a particular object. Let's say at temperature T0, density equals to mass divided by volume. So on temperature T, volume will become V naught 1 plus gamma delta T. On increasing or decreasing temperature, there will be no change in mass. So you'll say, and there will be no change in mass. So we can write density equals to mass divided by volume. Put the value of V to be above part. So you'll get M divided by V naught 1 plus gamma delta T. Now this particular ratio, mass divided by V naught, is nothing but rho naught. So we may write it as rho equals to rho naught divided by 1 plus gamma delta T, having exponential 1. So if you move this denominator to numerator, its exponential will become minus 1. So we may write it as rho naught 1 plus gamma delta T to the power minus 1. Now, according to binomial expansion, this raised power minus 1 will get multiplied with the coefficient of gamma. So we may write density equals to rho naught 1 minus gamma delta T. So from this expression, you will say on increasing temperature, density of particle or body decreases. Hence, on increasing temperature, density of body decreases. Atif, any doubt? Okay. You are done?
Done, sir.
Atif, done? Okay, we may write this particular expression in some other way also in terms of volume. Since delta V by V equals to gamma times delta T, and which will be equals to minus of delta rho by rho. If you simplify this expression, you'll get this part. This negative sign simply defines you if volume will increase, density will decrease, and vice versa. So this negative sign will define volume and density will increase or decrease and opposite of each other. But there will be some exception for this particular formula in case of water. Let me define you, which is called anomalous behavior of water. Suppose if you plot volume versus temperature, then density versus temperature. Riba, just tell me at what temperature density of water having maximum value? I defined you this part in fluid. Density of water will be maximum at a particular temperature. Nida, any idea? It will be maximum at 4 degrees Celsius. Suppose if you draw a vertical line at this particular point, let's say 4 degrees Celsius. So on going from 0 degrees Celsius to 4 degrees Celsius, volume of water will decrease and density of water will increase. So at 0 degrees Celsius, when it converts into ice, it may have lesser density and larger volume. But after this particular temperature, 4 degrees Celsius and above, on increasing temperature, volume will expand and density will decrease. So if you plot curve related to this part, at 0 degrees Celsius, it will have some larger volume. On increasing temperature, volume will start decreasing to this point, lowest, and then start increasing with rising temperature. So you will say at 4 degrees Celsius, it will have least volume. Similarly, in case of density, which is opposite of this volume. So it may increase to this part and then decreases with rise in temperature. So at 0 degrees Celsius, its value would be 998 kg per meter cube, but at 4 degrees Celsius, it will be 1000 kg per meter cube. Is it clear?
Yes.
Due to this behavior in ocean or river, there will be formation of ice on the surface of water at 0 degrees Celsius, but below it, temperature of water will be above 0, 1 degree, 2 degree, 3 degree, or 4 degrees Celsius, which having more density as compared to ice. And due to this behavior, enables aquatic life to survive on the surface of Earth. Okay. Reba, any doubt?
Sir.
Okay. Just write it down. You all have done?
Done, sir.
Now, next term is heating of liquid in a vessel. Suppose you have a vessel placed over burner. If liquid is filled initially up to this level, let's say A. So what will happen to this level of liquid initially on heating? Will the level of liquid increase or decrease on initial heating? We are considering before its evaporation. Riba, what will happen? Will the level of liquid increase or decrease, or it will remain same?
Decrease.
Decrease. Okay, why?
Because it will evaporate.
I've told you before evaporation of this liquid, initial heating.
It will remain same.
We are still heating it. So due to heating, it may expand. So will the level of liquid increase or decrease?
Increase.
Okay.
Abhinav?
Yes, sir.
Any guess? What will happen to the level of liquid in this vessel on initial heating before its evaporation?
It will increase, sir.
Okay. Atif?
It will increase.
Okay. Just think, on heating on this particular burner, we have two different material in this part. One is vessel and the other is liquid. So which one of them will get heat first? Vessel or liquid?
Vessel.
So everything on heating will expand first. So which will expand first? Vessel or liquid?
Vessel.
So if vessel would expand, level of liquid will increase or decrease?
Decrease.
Good. That is the reason behind it. So you'll say on heating initially, since vessel would get heated first, so it will get expand, due to which level of liquid first decreases, then increases due to its own expansion. Is it clear?
Yes.
So you'll say on heating, vessel will receive heat first, so get expand, hence level of liquid first decreases, then increases due to its own expansion. Now let me define its mathematical part. So on a expansion of vessel, level of liquid may reach to this point, let's say B. On further expansion of liquid, it may expand to this point, C. So on going from A to B, it will be due to expansion of vessel, but on going from B to C, it will be expansion of liquid, but we will observe only this part, A to C, which is called apparent expansion. So from this, we can say B to C is equals to A to B plus A to C. B to C is the real expansion of liquid. A to B is expansion of vessel, and A to C is apparent expansion. Is it clear?
Yes.
You all have written? Atif, done?
Sir.
Okay. So this is all about expansion or thermal expansion of solid and its related problem. Next topic in this particular chapter is calorimetry. Calorimetry is simply study of exchange of heat between any two different objects or two systems, which results in change of temperature or change of their state. So calorimetry is the study of exchange of heat between bodies or system which results in change of state or temperature is called calorimetry. So it's mainly based on conservation of energy. So you may define principle of calorimetry, which is based on conservation of energy. It state heat lost by one body or system must equals to heat gained by another body or system if there is no loss of heat in the surrounding. If there is no loss of heat in surrounding. Riba, is it clear?
Yes, sir.
Now, for this particular calorimetry, we may define heat in two parts. First, heat which causes to change in temperature. So it will be of three different types. First is heat capacity. Next will be a specific heat capacity. And molar specific heat capacity. Next part, if heat causes to change in state, so change in state will be of two part. First is latent heat of fusion. It means conversion of solid into liquid. Next, latent heat of vaporization. That is conversion of liquid to vapor. Atif, any doubt?
No, sir.
Okay, just write it down. Abhinav, is it clear till this part?
Yes, sir.
Okay. Abhinav, done?
Yes, sir.
Okay, let me define you these terms, what it means. First is heat capacity. It is the amount of heat required to change temperature of any substance by 1 degree centigrade. So heat capacity is the amount of heat is required to change the temperature of substance by 1 degree Celsius or 1 Kelvin at normal atmospheric pressure. So heat capacity Q equals to S times delta T. So this S is called heat capacity or simply heat capacity constant. So its SI unit related to this formula will be joule per Kelvin. Atif, is it clear?
Yes, sir.
Next, since in this part, there is no specific mention in this part, a specific mass, a specific amount. So if you define a specific term, so it is called specific heat capacity or specific heat constant. It states the amount of heat is required to raise the temperature of 1 kg substance by 1 degree Celsius or 1 Kelvin at normal atmospheric pressure is called specific heat capacity. So Q equals to mass of substance times specific heat capacity constant times change in temperature. So this S is called specific heat capacity. So its SI unit related to this formula will be joule per kg per Kelvin. Now, for this, we may define you some fixed value. In case of water, specific capacity of water is maximum, which is 1 kilocalorie per kg per gram per Kelvin. Suppose if you want to convert in terms of joule, 1 calorie equals to 4.186 joule. So we may write it as 4186 joule per kg per Kelvin. Atif, Is it clear?
Yes.
Similarly, specific heat capacity of ice, specific capacity of vapor is 0.5 calorie per gram per Kelvin. First, write it down till this part. You all have written. Similarly, third part, that is molar specific heat constant. Molar specific heat constant or capacity. In this part, or let's say this is defined only for gas. The amount of heat is required to raise the temperature of 1 mole of gas by 1 degree Celsius or 1 Kelvin at given condition. So basically, we have 4 different types of processes in thermodynamics: isobaric, isochoric, isothermal, adiabatic. So related to each different process, there will be different condition and there will be different molar specific heat capacity. That's why I've given, according to given condition, it may change. So Q equals to number of moles times C times delta T. So this C is called molar specific heat constant or capacity. So its SI unit will be joule per mole per Kelvin. Atif, is it clear?
Yes.
Now there will be relation between all these 3 terms which we have defined above. Capital S, that is heat capacity, equals to mass times small s, that is specific heat constant, and this should be equals to number of moles times C. So use this formula to convert or to find any of these terms. And this N is number of moles, which will be equals to given mass divided by molar mass. Okay, just write it down. Abhinav, any doubt?
No doubt, sir.
You have written to this?
Yes, sir.
Okay, so this is all about how to change temperature of a given substance, and we define different constants related to that part. Second is, if you have to change the state of that particular body, so we may define first latent heat of fusion. You must have learned about it in class 9th. Atif,
Yes, sir.
would you like to define it? Latent means hidden. It means if you start heating solid to convert it into liquid, let's say ice to water, so its temperature will not change up to entire liquid or entire ice get converted into liquid. It means on changing state from one to another, amount of heat supplied to that particular object get utilized in breaking of bond. So there will be no rise or fall in level of or temperature of that particular substance. That's why it is called latent or hidden heat. So we can say the amount of heat is required to change 1 kg solid into liquid at its melting point and normal atmospheric pressure. So Q equals to mass of substance times latent heat of fusion constant. So this LF is called latent heat of fusion constant. For ice, it is equals to 80 calorie per gram. Riba, is it clear?
Yes, sir.
Okay. Similarly, we may define latent heat of vaporization. The amount of heat is required to change 1 kg liquid into vapor at its boiling point and normal atmospheric pressure. So Q equals to mass of substance times latent heat of vaporization. This LV is called latent heat of vaporization constant, and in terms of water to vapor, it is equals to 540 calorie per gram. So just remember these values, which will be used directly in the different questions. Atif, any doubt?
So the constant for ice is 80, right?
Yes, Atif?
So the constant for ice is 80 or 50?
80 calorie per gram. It's 80.
Okay, sir.
Atif, done?
Yes, sir.
One last sentence related to this part. Just remember, during change of state, heat supplied to the system is utilized in breaking of bond. Hence, there will be no change in temperature. That's why it is called hidden heat or latent heat. Okay, you all have written?
Mm. That's
Okay, so in all of the above expression or definition, I define you at normal atmospheric pressure and at a given condition. So in next class, I will define you its effect on changing atmospheric pressure and its various other application as well. And next class, I will define you how to solve problem related to this entire calorimetry. Okay. So just revise this whole part and try to do different problems related to this. Okay. We'll continue next class.
okay, sir. Thank you, sir.
Thank you.